Hello everyone! Today we are going to learn how to represent models of dynamical systems using transfer functions. For example, what you can see over here is a simple mass spring damper system that can represent the dynamics of a large number of mechanical and electrical systems. A differential equation representing the dynamics of such a system is given by the following equation, where m is the mass, kd is the damping constant, ks is the spring constant, b is the control force constant, f is the control force, c is the disturbance constant, and d is the disturbance force. Of course, x is a displacement of the mass from its equilibrium position. The purpose of the control force F is to steer the mass to a desired position. So, for example, this can be a desired position of the mass. At the same time, we assume that there is a disturbance force acting on the system. The goal of this video is to teach you how to transform this ordinary differential equation, that's basically a system model in time domain, into a transfer function form. That's basically a system representation in the complex domain. So, in the transfer function representation, the model of this system will have the following form. We will have the control input force, or the control force F. Then we are going to have a transfer function from the control force to the displacement x, and at the same time we're going to have another transfer function that models the effect that the disturbance force D has on the output x. These two influences are modeled by the block diagram that I sketched over here. W1 and W2 are transfer functions. W1 is a transfer function from control force to the displacement, and W2 is a transfer function from the disturbance force to the displacement. You can notice here that I added a plus sign. Right. So, from a mathematical point of view, this block diagram corresponds to something that looks like this, to an equation that looks like this. X of s is equal to W1 of s times F plus W2 of s times D. Again, W1 and W2 are system transfer functions. Then, in this video, I will teach you how to simulate the response of this system to control force and to disturbance force. What you can see over here is the oscillation of the system when you apply a constant force that's equal to 1. So once you basically apply a constant force, you pull this mass continuously in one direction, your mass will oscillate, and after some time it will settle at certain position. Similarly, if you apply a disturbance force D, and if you keep this disturbance force constant and equal to 1, for example, your displacement will behave like this. It will similarly oscillate and it will settle at certain position. In addition to this video, I have created a post that nicely summarizes everything that I will explain in this video. So you can find all the equations, all the graphs, and all the codes that I will explain in this video. A link to this post or web page is given in description below. Okay, so first I'm going to explain how to transform this ordinary differential equation into a transfer function form. In control theory and in control engineering practice, we often use two different forms of transfer functions. These two forms are equivalent. The first form looks like this. In this representation, S1 and S2 are the poles. The poles are the zeros of the polynomial in the denominator of your transfer function. The second form looks like this. What is interesting about this representation? As you will see later in this video, the number g or the parameter g in the numerator of the transfer function is the system steady state gain when an input that's equal to a step signal is applied to the system. So from this representation you can directly see the steady state system gain. And moreover, I'm going to call g as a gain here, and moreover, tau 1 and tau 2 are related to time constants of the system, as you will see later in this video. Okay, so let's start. The first step is to divide this equation by m. As the result, we obtain this equation. The next step is to take the Laplace transform of both sides. Now, since the Laplace transform operator is a linear operator, we obtain Now, again, since the Laplace transform is a linear operator, these constants inside of these brackets can go out. So Laplace transform of kd over m times x dot is nothing less than kd over m Laplace transform of x dot. Similarly, we obtain the Laplace transform of ks over m times x is equal to this term, and the other terms are obtained or transformed using the same principle. Let us introduce a new notation. So, Laplace transform of x will be denoted by x of s. Similarly, Laplace transform of the force F will be denoted as f of s, and the Laplace transform of the disturbance force D will be denoted as d of s. Good. Now, the fundamental question is, what is the Laplace transform of x2 dots, and what is the Laplace transform of x dot? To answer these questions, we need to use the following formula. So, this formula tells us that if we take the Laplace transform of the n derivative of a time function x of t, we will obtain something that looks like this. So it's equal to s to the power n Laplace transform of x of t, that's denoted by x of s, and we have in addition these terms over here. This is basically the initial condition, and then this is the derivative of the function evaluated at the initial condition. This is the second derivative of the function evaluated at initial condition, and this is the n-1 derivative of the function evaluated at 0. So let us simply apply this formula to Laplace transform of the second derivative of x dot and to the first derivative of x dot. So we obtain here n is equal to 2. So we obtain good. How about Laplace transform of x dot? In this case, n is equal to 1, so we obtain and I'm going to skip a few steps and I'm going to simply to write the final expression. Since this is n is 1, this becomes s to the power 0, and we simply have minus x of 0. Now, transfer functions of dynamical systems are defined for one particular case. They are defined for the case in which the initial conditions are equal to 0. So, to define a transfer function, we need to assume that x of 0 is equal to 0 and that x dot of 0 is equal to 0. So, these terms in the final expressions disappear. So finally, in this particular case, in the case for which we want to derive transfer functions, we obtain and these two expressions are the final expressions, and they need to be substituted in our original equation. So we obtain now, From this equation, we can see that x of s can be taken out of these three expressions and can be represented as something that looks like this. Okay, now if we divide both sides of this equation by this term, we will obtain this function is nothing less than our w1 of s, and this function is nothing less than w2 of s. So we have obtained that x of s is equal to w1 of s times f of s plus w2 of s times t of s. The next step is to show how to transform this transfer function into the form that looks like this, where tilde s1 and tilde s2 are given by this equation. Tilde s1 and 2 are actually the poles of the system. They are the zeros of this polynomial. To achieve this, we need to recall one basic technique that you learned in calculus. And this technique is called the computation of squares. So the basic problem is, if we have a polynomial that looks like this, we want to factorize such a polynomial. That is, we want to write it as s minus s1 times s minus s2. How to achieve that? Obviously, to transform w1 from this form into this form, we need to factorize this polynomial. So, how to factorize this polynomial? Well, I'm going to skip here a few steps in interest of making this video relatively short. So the problem boils down to factorizing a polynomial that in the general case looks like this, where b and c are constants. In order to factorize this polynomial, we can use the computation of squares trick. So we can write p of s is s squared. So this term is just written as 2 times 1/2, and I deliberately added here 1 over 4b squared, and I've subtracted 1 over 4b squared, and I added c. So these two forms are equal to each other. Now, if you recall the quadratic formula, these three terms can be written as s plus b over 2 squared, and you can leave, or you can group these two terms into the following term. Right. Now, we can recall the following formula. P squared minus q squared is p minus q multiplying p plus q. And if we apply this formula to this equation, taking as p this term over here and as q this term over here, we will obtain this formula. So this is the final expression. The expression that you can see over here corresponds to here. We just transform this and we obtain something that looks like this. Now, we can simply rewrite these terms in brackets. We can write them as minus. We add here minus. And what do you see here? What do you observe? This is the final expression for factorized polynomials. Now, if you recall a basic formula for finding zeros of a quadratic equation, you will see that these two terms are basically zeros of a quadratic equation. Basically, the zeros of the equation s squared plus bs plus c is equal to 0. So, what did we learn? The problem of factorizing the polynomial is equivalent to the problem of finding zeros of a quadratic equations. And what is the general form of your factorized polynomial? The factorized polynomial looks like this: s minus s1, s minus s2, where s1 and 2 are given by this formula. If we apply this general principle to our constants, the constants of this equation over here, the equation over here, we will obtain this formula. So these s1 and 2 tilde will be zeros of the expression in the denominator of the w1 of s. Actually, doesn't matter, w1 and w2 are actually the same functions. So this is the way for factorizing the polynomials. The procedure is, again, compute zeros of these zeros are denoted by s1 tilde and s2 tilde. Then you can simply write this polynomial as Let us now explain how to transform w1 of s from this form into this form. To make this transformation, we will start from this form of the transfer function. Now, let us analyze this form. If we take out from the first bracket minus s1 tilde, inside of the bracket we will have 1 over minus s1 tilde times s plus 1. Similarly, if we take out of the second expression minus s2, inside we will have 1 over s2 times s plus 1. Now you can immediately see that this term is tau 1 and that this term is tau 2. Now, how about a? If you remember, the form of the transfer function that we are looking for is the following. What is a equal to? Well, if you see our original expression, a should be equal to b over m divided by minus s1 tilde multiplying minus s2 tilde. Now, after some massaging and taking into account the derived expression for s1 tilde and s2 tilde, remember that s1 tilde and s2 tilde are zeros of the original polynomial in the denominator of the transfer function, we will obtain that our expression for a has the form equal to this term. That is, a should be equal to b over ks. Similarly, you can use the same trick to represent w2 function into the form that looks like this. In this case, b will be equal to original term in the denominator, or actually in the numerator of the expression. Let's see what was that. This was basically c over m, right? Here is the term. It should be c over m. So in our case, RB should be equal to c over m divided by minus s1 tilde multiply minus s2 tilde. And after some massaging and few transformation, you can obtain that b is equal to c over ks. Let us now see how to simulate this system in MATLAB. Well, first I'm going to define three parameters that define the system dynamics. These parameters are the mass, damping, and the spring constant. I choose these values. In your simulations, you can arbitrarily change these values. Then I assume the control force constant to be equal to 1, and I'm assuming the disturbance constant to be equal to 0.1. Next, I define transfer functions. So how are transfer functions defined in MATLAB? Well, in MATLAB, we define transfer functions as polynomials. For example, let us assume that I have this transfer function. Okay, this is S here. Now, to define these transfer functions in MATLAB, I would need to define two vectors. The first vector will be the polynomial, actually the coefficients of the polynomials in the numerator. In this case, the coefficients will be k1 and k2. So this corresponds to the polynomial that looks like this. Similarly, the expression in the denominator will correspond to a vector, and its entries will correspond to coefficients of the denominator, actually the coefficients of the polynomial in the denominator. So these coefficients will be c1, c2, and c3. Okay, if we go back to our case, to our transfer function, and to our system, we will obtain that our W1 has the following form. So its coefficients, or the values of the polynomial in the numerator and the denominator, will correspond to a vector. So the numerator in this case will be b over m, and the expression in the denominator will be 1 kd over m and ks over m. Here is how we define these two vectors in MATLAB. Here is our numerator and our denominator. And we use the MATLAB function tf. T stands for transfer, f stands for function, so tf is the transfer function. As arguments to this function, we specify the numerator and the denominator. And by executing this line of code, we have obtained our transfer function. So here is our transfer function. Similarly, we can define W2 transfer function from disturbance force to position. And let's check the poles. Let's check the poles of the first transfer functions. Remember, the poles are the zeros of the polynomial in the denominator. So these zeros are given by these two values, and the function, the MATLAB function for computing the poles, is nothing less than pole. Pole W1 will give you the poles of the system. Now, if you remember, if you go back to our slides, we have actually computed the poles, right? Here are our poles. Now, in MATLAB, we can simply compute these poles starting from our parameters, and we can verify, right? We can verify that our numerically computed poles correspond to poles given by MATLAB. So our calculations are 100% correct. Okay, here's another way for defining transfer function. Right. So instead of using numerator and denominator vectors, right, or coefficients of the polynomials in the numerator, in the denominator that are grouped in a vector, I can simply use the following trick. And this trick will be explained on the second form of the transfer function that's given by the following equation. Okay, so I define tau1 and tau2 as 1 over poles, right? These are 1 over the system poles, and I define A and B. Now, I use this MATLAB command, right? This is the command for defining, for saying that S is now a transfer function, right? TF of S, this is a symbolic expression, so this gives you S as a transfer function. So if we type S, continuous time transfer function, S is equal to S. And I can now simply and symbolically write the form of the transfer function. So my transfer function is 1 over, in the denominator, tau1 times S plus 1 times tau2 times S plus 1. So here are these two expressions. Okay, let us compare. So this is our W1 original, and we have W1 other form. Do they look equivalent? Are they the same? Well, from these two expressions, they don't look that they are the same. However, we can compute the pole. We can compute the pole of V1, this is what we obtain, and we can compute the poles of V2. Voila! The poles are the same. So this is another way, and I think this is an easier way for defining transfer functions. Let us now explain how to simulate the system response. How to simulate the system response? Well, the first step is to define the simulation time. The simulation time is a time period during which we are going to observe the system behavior. And we are going to apply a step input, meaning that the control force acting on the system, this control force, will be equal to a unit value and will be kept constant during this time period, right? This is a step response. Let's see what do we obtain. The MATLAB function for computing the step response is the step, you specify the transfer function, you specify the simulation time, and let's see what do we get. Here is our step response. Here is our step response. On the x-axis is time, on the y-axis is the displacement. Let's see where our system settles. The system settles, believe it or not, at the point 0.01, and this point, if you look at the other form of the function, corresponds to the system, to the value over here. So our system is basically decreasing the value of the input force. So the input force you want basically to be 1. However, at the response, this displacement becomes equal to 0.01. So this is some kind of attenuation of your input force in your system. It's not actually the attenuation of the force. However, the force or the gain can be defined as the basically ratio of the displacement over the force, right, is equal to 0.01. Similarly, you can obtain the step response with respect to disturbances, and you will observe that the disturbances settled at the point 0.001, and from the second form of the transfer function you will see that this point approximately corresponds to the value in the numerator. Okay, today we learned two important techniques for representing transfer functions of dynamical systems. I hope that you like this video, and if you like this video, please subscribe or support this channel. Thank you for your time and have a nice day.